Hey class, so this chapter was entitled Radical and Rational Functions. And so throughout the chapter we have looked at all aspects of both types of functions. We've looked at simplifying both radical and rational expressions. We've looked at graphing both radical and rational functions. And we've now come to the point where we're going to be solving radical equations and inequalities just like we solved rational equations and inequalities. So we've kind of come full circle, looked at all aspects of these types of radical and rational functions. So the focus of today's lesson is very simple, just one learning goal, to solve radical equations and inequalities. So as a rule, there's usually two steps in solving a radical equation, and the first step is to isolate the radical. So that means to get the part of the equation that has the radical all by itself on one side of the equation. And the second step is to raise both sides to the power of the radical. So that sort of sounds funny because the radical really is a root. So what we really mean is like the index on the radical. So whatever, so this actually should say the radical's index. So whatever the index is, that's what power we want to raise both sides to. And that's because then the power will cancel out the root. And in effect, get rid of the radical, which is the thing that's really keeping us from solving the equation and getting x, the unknown, all by itself. So let's take a look at these two steps in the context of a few examples. So example 1 says to solve it's actually solving equations containing one radical. So it says solve each equation and check your answer on your calculator. I guess you could also check it manually if you'd like. So the first step was to isolate the radical. So I want to get this piece, the radical piece, all by itself. And so I'm going to have to get rid of the 5 that's being added to it. So I'm going to subtract 5. Well, that leaves me with the radical all by itself, which was my goal in step 1. And on the alternate side, I have 16 minus 5, which is 11. Now the second step was to raise both sides to the power of the radical's index. So the radical's index is actually 2 because it's not written, so it's implied that it's 2. So we want to raise both sides to the second power, and here's exactly why we're doing that. By raising both sides to the second power, we're going to cancel out the radical on the left-hand side, and it just leaves us with x plus 1. And on the other side, we have 11 squared, which is 121, and now we have a very simple equation to solve. We just have to get the variable all alone by subtracting 1 from both sides, and that tells us the x must be 120. Now we want to check it, and again you can put that in your calculator if you want, but I'm going to check it manually. And so I'm going to plug it back in the original. So 5 plus the square root of 120 plus 1 equals 16. And 120 plus 1 is 121. The square root of 121 is 11. So that makes 5 plus 11 equals 16, and that checks. Now, as we saw when we were solving these rational equations, we saw that there were sometimes these things called extraneous solutions. And extraneous solutions happened with the rational equations when we came up with a solution that would make the denominator 0 or undefined. And so that means, so that in other words, it made the equation undefined because it made the denominator 0. Well, in the case of these, there are also possibilities that you might have extraneous solutions. So it's always a good idea, and it should be kind of paramount, something that you always do with these, is to check your answers. Let's go ahead and take a look at example B. So again, the step 1 is to isolate the radical. Well, this is the radical part. It's the cube root of 5x minus 7. And what's with it is this 7 being multiplied. So we're going to undo it by dividing by 7. And that'll get this radical, this cube root part, all by itself. And on the other side, I'll have what 84 divided by 7 is, which is 12. Now step 2, we said we're going to raise both sides to the power of the radical's index. And so what we're going to do is we're going to raise both sides to the radical's index. Well, that was a radical 3 or cube root, so we're going to raise both sides to the third. We're going to undo cube rooting by cubing. So when we cube the cube root, it just cancels out the radical and leaves us with this radicand of 5x minus 7, excuse me. And on the alternate side, when I raise 12 to the third power, I get 1,728. And now it's just simply to go through the steps to solve, to get x alone. So I'm going to add 7 to both sides, and that leaves me with 5x equals 1,735. And then I'm going to divide both sides by 5, and I get a solution of x equals 347. So now I've got to check that. So if I go back to this original, I want to know what 7 times the cube root of 5 times 347 minus 7 is. I want to see if it actually is equal to 84. So I take 5 and I multiply it by 347, and 5 times 347 is 1735. So that's 7 times the cube root of 1735. And when I take the cube root of 1735 minus 7, which then is 7 times the cube root of 1728, and the cube root of 1728 is 12, and 12 times 7 is 84, so it checks. So far so good on our checks. Our algebra that we did in the equation held up when we substituted it back into the original. And as we saw in the earlier lessons, that's not always going to be the case. So you want to make sure, whether it be that you just are typing it in the calculator to check it, or that you're actually manually checking it like I did, that you are actually checking it. So we're going to designate C a you-try question. So this is your opportunity to test out the two-step process of solving radical equations. So pause the video now and solve and check the equation in example C. So x is equal to 39, and as you can see, I checked it, and I hope you did too. Let's go ahead and turn the page. So our next example is solving equations that contain two radicals. So when we have two radicals, we're not able to do that very first step of the two-step process, which is isolate the radical, because we have radicals on both sides, and there's no way to isolate a single radical. And so basically the steps just sort of move up to the next level. So we move up to step 2 when we can't do step 1, and we go from there. So we're going to raise both sides to the power of the radical's index. In other words, these are square roots, so we're going to square both sides. So I'm going to go ahead and do that. I'm going to square both sides. I'm going to go right straight to step 2. But this time the part that makes it a little tricky is that on the right-hand side I have a 3 that's going to be squared also. So that 3 squared part is 9. I have to square that. But then I can square the square root of 3x minus 2, and that just cancels out the squared. So that leaves me with 3x minus 2. So by squaring this whole thing, the radicals canceled out, and the coefficient, the number in front, is squared. On the other side, it just cancels out the radical, and it leaves me with 7x plus 2. And now I do have an equation I can solve. It's a little tougher than the ones we've been solving, but definitely not something that we haven't seen before. So now we could distribute the 9 through to both parts, and that gives me 27x minus 18 equals 7x plus 2. And now we want to start moving the variables to the same side and the real numbers to the other. So I'm going to subtract 7x from both sides. That leaves me with 2 over here and 20x minus 18 over here. Now I'm going to add 18 to both sides, and that leaves me with 20 is equal to 20x, and of course we're going to divide by 20 then, and that's going to give us just 1. So that means x equals 1. Now again, I want to check it, make sure, so I'm going to plug it back into the original, and so I know that the square root of 7 times 1 plus 2 is supposed to equal, we want to know if it does, we don't know for sure, got to check it, 3 times the square root of 3 times 1 minus 2. So 7 times 1 is 7, plus 2 is 9, so that's the square root of 9. Is supposed to equal 3 times the square root of 3 times 1 is 3 minus 2 is 1, square root of 1. So this equals 3, and the other side equals 3, so it checks. So let's make B a you-try question. So please pause the video now and follow the example of that we did in example A there, and complete example B. So pause the video now. So in this example, the answer for x is 6, and you can see that I checked it. You could also just check it by getting the decimal equivalents, but I showed how if you simplified what the left-hand side would be, which is the square root of 54, just you put it in simplified radical form, then the two sides would be equal. So let's do one more together. So with this one, example C, this time the index on the radical is a 3. So I'm going to cube both sides this time. So I'm going to raise both sides to the third. And so when I raise this side, the left-hand side to the third, that's just going to cancel out the radical and leave me with x plus 6. And on the other side, I'm going to have to cube the 2 and cube the cube root. So when I cube the 2, that's 8. When I cube the cube root, that leaves me with just x minus 1. The radical cancels out, and now what's left to do is distribute the 8 and then solve this. So if I distribute the 8 through, that's 8x minus 8, and that's supposed to equal x plus 6. So now all we have to do is bring variables on one side and, of course, the real numbers on the other. So this would leave me with a 7x minus 8 on this side. I could add 8 to both sides, and that gives me 14 equals 7x. So x, when I divide by 7, must be x is equal to 2. And again, I want to check it. I want to make sure, so far all of them have checked. And so I'm going to go ahead and just type this in my calculator this time. And if you want to take a second, pause the video and check it, but I'm going to just plug it right in there. And when I do that, that's the cube root of 2 plus 6, or 8. That's 2, so that makes the left-hand side 2. And when I plug it in here, I'm multiplying 2 times the cube root of 2 minus 1, which is 1. So it's the cube root of 1 is 1, and so 2 equals 2. And so that checks. All right, let's go ahead and turn the page. Now we talked about these extraneous solutions, but here's a little tip on when these occur. Raising each side of an equation to an even power may introduce extraneous solutions. So when we're thinking about these extraneous solutions, when we might anticipate they could occur is actually in this situation when we're raising both sides to an even power. Now, the reason why that can occur is, we've come across, the situation where we might be trying to take a square root of a negative number. That gives us an imaginary solution. And so in some cases, there are certain square roots that we just can't take. Or when we take a square root or a fourth root or an even root of whatever, you could get a positive value, you could get a negative value. And so that's why the issue arises when we're dealing with even powers. Because squaring something that's positive keeps it positive, squaring something that's negative makes it positive. And then taking even roots, then there's inherent in that there are some issues with positives and negatives. So we're going to go ahead and utilize our technology, our graphing calculator, to have a little better understanding of when these extraneous solutions occur. So if you don't have your graphing calculator, pause the video now and go and get it. So taking a look at this example, we're asked to solve the square root of negative 3x plus 33 equals 5 minus x. Now, one way to solve an equation is to utilize your graphing calculator. So if we were to take and put in our grapher the left-hand side in y sub 1, it's kind of hard to see, but they're actually underneath that cursor is a square root right there, so you can't see it very well. But so we took the square root of negative 3x plus 33 and put that under y sub 1, and then we'll take the other side and we're going to put that in y2. And what we want to know is when they're equal, so we want to look to see on the graph where the two lines would, or the two graphs, one's a curve, will cross. And then in the table, we want to see when the outputs are the same. So that's what we're kind of looking for. So I went ahead and put it in, graphed it, and took a picture of it. And this is what I saw. So I saw my square root graph, which is this one right here in the red. I'm going to highlight that one in the red. So remember that those, we usually just look at one of the branches, so it looks like this, like half a parabola turned on the side. And so that's as far as it actually goes. It actually cuts off there. And then we have the line, which is here. And if we look in the, well, there's that spot we think that looks like the solution is there. And if we look in the table right around that same place, we can see that at -1, there's the same output. The output is 6 for each one. So I only see the graphs actually crossing once. So I would say, if I was solving it using the calculator, that the solution is x equals -1, because that is the one place where I see the graphs crossing and the one place in the table where I see the outputs are the same. Now let's take a look at how that would look if we solved it algebraically. Okay, so I rewrote the equation, and solving this algebraically would require me to, since I have the radical isolated, I'm going to raise both sides to the power of the index of the root. So that means I'm going to be squaring it. That's how I undo a square root. So I squared both sides. Well, on the left-hand side, that'll cancel out my radical, leaves me with -3x plus 33. But on the right-hand side, by squaring 5 minus x, that means I'm multiplying 5 minus x times 5 minus x, because there's two of them. And that's what squared really means. So then I'd have to use FOIL. So if I used FOIL and I multiply these out, first outside, inside's last. First two, 25, outside 2 minus 5x, inside 2, I'll rewrite that in red so it'll show up a little better, inside 2 minus 5x, last 2 plus x squared. Now maybe I want to turn it around and put my like terms together because I'm used to having it in standard form. So that would be x squared and then minus 10x. That background's a little dark for that marker. And then plus 25. But on the other side I have minus 3x plus 33. So if it's a quadratic, which I can see it is, then my strategy is to get everything on the same side. And so to get everything on the same side, I'm going to add 3x to both sides. So I'll go here and add 3x. And then I'm also going to be subtracting 33 from both sides. And that's going to leave me with a 0 on the left. And on the right I have x squared minus 7x. Write this whole thing in red. Minus 7x. And then I have a minus 8. So now I'm going to try to factor this. So when I write the factors, they're going to both start off with x. And they've got to end with two numbers that multiply to -8 and add to -7. So I'm thinking right away of -8 and +1. And so since they have to equal 0, that means that my two solutions that I'm coming up with are x equals 8 and x equals -1. But on the graph, we only found one. We only found one value. So what that's telling me is that means that one of these solutions, this one right here, must not work. And here's why it doesn't work. If you were to take that and plug it into the original, if you took that 8 and plugged it in right there, under your radical, you'd have -3 times 8, which is -24 plus 33. That would actually make the square root of 9, but on the other side we have 5 minus 8, which is -3. So when we think of the principal root of the square root of 9, we think of 3, but it's saying that the square root of 9 is -3. And so that one actually doesn't check, and that's why you don't see the graph crossing down where it would x would be 8. That would mean if this graph had to continue on and went down, this is where it would cross down here where x was 8. But it doesn't because that has that restricted domain. So by that graph cutting off right here and not going any further, it doesn't actually get down to where x is 8 to actually cross the line 5 minus x. So we just have one solution here, and we call the solution of x equals 8 to be extraneous, and only x minus 1 works. And so we can graph and verify that with our graph. So we're going to designate example B as a U-try question. So you want to try to solve this both ways. Take a look at your calculator, see if you can identify how many and where the solutions would be, and then solve it also algebraically so you can see whether there actually were extraneous solutions or not. So please pause the video now and solve equation in example B, both methods, with the calculator and also algebraically. Okay, so I just did a quick little sketch of what your calculator graph would have looked like, and I used the table to find the place where the two lines or the two curves crossed. Excuse me. So I could see that the curve, the square root curve, it stopped right there on the x-axis. It didn't go any further, and so this isn't going to continue down. It's not going to hit that line again. It only hits it in one spot, and it actually hit it at x equals 1. And that would really make sense if you plugged 1 in back into the original, it works. So the other place that when I solved this algebraically that I found that should have worked was x equals -5. And I kind of went through that whole process of squaring both sides. But what happens is when I plug -5 in, then what I'm getting is the square root of 4 equals -5 plus 3. And that's -2, so I'm getting the square root of 4 is equal to -2. Well, usually, unless we have the negative out in front of the radical, we're talking about the principal root, which is the positive root. And the only way that this would actually happen and this would cross again is if we had the other side, the unrestricted square root, and we came back around and this hit again, and that would be hitting at that -5, but then this wouldn't be a function. So because that doesn't, your square root, you don't see both branches of the square root function, then you don't see that second place where it's crossing. It causes that extraneous solution. So just one solution, x equals 1. Let's go ahead and turn the page. So we're going to designate example C as an in-class. So we had one we did together. I had you try one independently. We'll try C together in class just to make sure if there was anything that was tricky about that or that you struggled with when you did the U-try, we can discover that when we do example C together in class. So let's look at example 4. So example 4 asks us to solve equations with rational exponents. So if you look at example A, we want to know the value of x. That would make 5x plus 7 to the 1/3 power equal to 3. And so remember that raising something to the 1/3 power is really just the same thing as cube rooting it. So one thing I could do is rewrite this as a cube root, and that, then solve it by raising both sides to the 3rd power, but that really is sort of an unnecessary extra step because since I know that this is a cube root, I can really just raise it to the 3rd, which is the reciprocal power of 1/3. So if I just raise both sides to the 3rd, that will cancel out the 1/3 as a power, because when you raise a power to another power, we multiply, and multiplying reciprocals of each other will just produce 1. And so by just raising to 1/3, this turns the left-hand side into 5x plus 7, and the right-hand side, 3 to the 3rd, is 27. And so then all I have to do to solve is just simply subtract 7 from both sides and divide by 5. So that means that 5x must be equal to 20 and the x must be equal to 4. So as usual, I want to make sure I'm checking these. So what I want to see is if 5 times 4 plus 7 raised to the 1/3 power, we want to see if it actually equals 3. So 5 times 4 is 20 plus 7 is 27, and 27 to the 1/3 power is 3, and so it does check. Okay, so using that same strategy in example B, this time I have 4x plus 8 being raised to the 1/2 power, so to undo the 1/2 power, I'm going to raise to the 2/1, or the 2 power, which means I'm really squaring both sides. So if I square the left-hand side, 2x squared is 4x squared. And if I square the right-hand side, it's just going to cancel out that power of 1/2 because I raise a power to a power.
makes a exponent of 1. 1/2 times 2 is 1. And so that just leaves me with the 4x plus 8. Now in this case, because this is quadratic, my goal is to try to group things on the same side together. So I'm going to subtract 4x and 8 from both sides because I'd rather bring the other things over where the x squared is so that my leading term is positive. And so when I do that, this is what I end up getting for an equation. Now I might think that maybe this is going to be one that I'm going to have to factor using the AC method, but you may notice that every single one of these terms is actually divisible by 4. So I could factor out that 4, and then what would be left is x squared minus x minus 8, minus 2, and then I could just simply divide both sides by that 4 and just get rid of it. And that would just leave me with x squared minus x minus 2 equals 0. And now I could factor this. So I'm looking for factors that multiply to -2 that add to -1. So of course that's going to be a -2 and a +1. And that means my solutions are 2 and -1, or my potential solutions, I should say. So what we got to do is make sure we check these. And so let's see if we plug them back in, will they both work? As I checked the two solutions, the -1 did not work because one side produced a -2 and the other side produced a +2. So the only one that did checks, and so my final answer is the x is equal to 5. The other solution was an extraneous solution. So I'd like to have you pause the video and try example C as a you try question, and be sure to check your answer. Go ahead and pause the video now. So x turns out to be 22, and it does check. So just one solution, x equals 22. Let's turn the page. So the learning goal target in example 5 is really, utilizing your graphing calculator to solve some radical inequalities. And due to the technical aspect of this and the fact that not everybody might have access to a graphing calculator at this point, then we're going to go ahead and save this example, and we'll do this together in class. So both example A and B will be in-class examples. And so we'll move on to our final example, example 6, which is an application. So here's our problem. It says the speed s in miles per hour that a car is traveling when it goes into a skid can be estimated by using this formula. S is equal to the square root of 30 FD. So where F is the coefficient of friction and D is the length of the skid marks in feet. So a car skids to a stop on a street with a speed limit of 30 miles per hour. The skid marks measure 35 feet. So remember that the skid marks were D, so this is right here is D. And it says, and the coefficient of friction, which is that is the part that was the F. And then you want to know, was the car speeding or not? So the speed limit on that street was 30 miles an hour. So we can calculate the speed using this formula, and then we can compare it to what the actual speed limit is. So to find that out what that is, we're going to take a look at the formula 30, or the square root of 30 times F times D. Well, if the friction is 0.7 and the distance or the length of those skids are 35 feet, and we multiplied those all, that ends up with the square root of 735. And so when we go ahead and take the square root of 735, we get approximately 27.1. Now remember the S represented right here in miles per hour. So that's 27 miles per hour. So the question is, was the car speeding? No, the car wasn't speeding. It was going less than the 35 mile an hour, or the 30 mile an hour speed limit that was indicated. So this wasn't really a problem where we had to actually solve a radical equation. It did utilize a radical, but in this case it was just really evaluating that radical equation and then answering the real life question. So that actually does it for today's lesson. And so when we meet again, we'll pick up where we left off, and we'll take a look at some of those things that we reserve for in class. So I'll see you then.